In question 31, it says that pressure versus temperature graph of 2 moles of neon gas is as shown in figure. The ratio between heat absorbed and change in internal energy of gas in process 1 to 2 is. So as you look at this graph, from this graph we can say that pressure and temperature will be directly proportional to each other because the graph is a straight line passing through origin. So pressure will be directly proportional to the temperature, and when pressure is directly proportional to temperature, we can say that volume will remain constant, and if the volume remains constant, so we can say that work done will be 0. So according to the first law of thermodynamics, Q will be equal to work done plus delta U, but since work done is 0, so we can write Q will be equal to delta U. That means heat will be equal to the change in internal energy. So question says the ratio between heat absorbed and change in internal energy. So that means Q by delta U will be equal to 1. So our option number 1 will be the correct option. Let's move to the question number 32. In question number 32, it says that a monatomic gas at pressure P having a volume V expands isothermally to a volume 3V, then compresses adiabatically to the volume V. The final pressure of the gas is. So according to the question, first it expands isothermally. So we know that for isothermal process, PV will remain constant initially. So initial pressure is P, initial volume is V, final volume is 3V. So we can write P into V will be equal to the final pressure into 3V. So from here we can say that our final pressure at the end of the isothermal process will be equal to P by 3, right? So this is our first step, that is isothermal process. So we can say that for isothermal process the gas changes from P comma V to pressure P by 3 and volume 3V. This is for isothermal process. Now question says that then compresses adiabatically to volume V. So again this gets compressed adiabatically to a volume V, but we don't know the pressure. We have to calculate the final pressure again. So this is for isothermal and this is for adiabatic, right? So we know that in adiabatic process PV to the power gamma will remain constant, right? So since it is monoatomic gas, we know that for monoatomic gas, gamma is equal to 5 by 3. So initial pressure is P by 3. So we can write P by 3. Initial volume is 3V. So we can write 3V to the power 5 by 3. Final pressure, we don't know. But we know the final volume is again V. So we can write V to the power 5 by 3. Right? So if I solve it, we will get P final will be equal to P into 3 to the power 5 by 3, because this volume and this volume will cancel out, divided by 3. So we will get P into 3 to the power 5 by 3 minus 1. So we will get P into 3 to the power 2 by 3. So this is our final pressure at the end of the adiabatic process. So my option number 2 will be the correct choice. Now let's move to the question number 33. In question number 33, it says that for a certain process of ideal diatomic gas varies according to the relation P is equal to AT square, where A is a constant. What is the molar specific heat capacity for this process? So first, since pressure and temperature relation is given, we have to convert this into pressure and volume relationship. So P is equal to AT square is given, and we know that PV will always be equal to nRT. So if I replace the temperature, we can write A into PV by nR whole square. So by solving, we can say that P square V square by P will remain constant. So square and P will cancel out. So we can say that PV square will be constant. This is our equation, modified equation, right? But we know that for any polytropic process which is in the format of PV to the power x is equal to constant, for any process PV to the power x is constant. This is called the polytropic process. For this process, the molar heat capacity is defined as R upon gamma minus 1 plus R upon 1 minus x. This is our for any polytropic process. But as we compare this equation with this equation, we can say that x will be equal to 2, right? And since it is a diatomic gas, so we can say that gamma will be equal to 7 by 5. So if I put the value of x and gamma here, so we can say that molar heat capacity will be R upon 7 by 5 minus 1 plus R upon 1 minus 2. So you will get 5R by 2 minus R, that will be equal to 3R by 2. So this is our molar heat capacity. So we can say that our option number 3 will be the correct choice. Now let's move to the question number 34. In question number 34, it says that an ideal gas is taken through a cyclic thermodynamic process through 4 steps. The amount of heat given to the system in these steps are Q1 1000 joule, Q2 minus 800 joule, Q3 450 joule, Q4 minus 200 joule. The efficiency of cycle. We know that the efficiency of any cycle will be given by 1 minus heat rejected by heat absorbed. This is the formula of the efficiency, and if you want to express it in percentage, so we should multiply it with 100. That will give you the percentage, right? So we know that when the heat is positive, it is the heat absorbed, and when the heat is negative, that means it is rejected by the gas, right? So if heat is given to the gas, then it will be positive. If it is taken from the gas, it will be negative. So here Q2 and Q4 are negative. That means this is the heat rejected, and Q1 and Q3 are positive. That means they are heat absorbed. So if I write it like this, so we can write 800 plus 200. This is the heat rejected divided by 1000 plus 450. This will be our heat absorbed into 100. This will be the efficiency. So 1 minus 1000 by 1450 will into 100. So you will get 45 divided by 145 into 100. So this will be approximately 31%. So we can say that our option number 1 will be the correct choice. Now let's move to the question number 35. In question number 35, it says that a refrigerator whose coefficient of performance is 6 extracted heat from cooling compartment at the rate of 300 joule per cycle. How much heat per cycle is rejected in the room? So we know that the coefficient of performance of any refrigerator will be equal to the heat extracted from cooling compartment. That means extracted from the sink. So Q extracted divided by work done by the external agent on the refrigerator. That means work done by the refrigerator, right? So this is Q by W. So according to the question, performance is 6, beta is 6, and heat extracted is 300 joule per cycle. So 300 divided by work done. So from here we can say that work done on the refrigerator will be equal to 300 by 6, that will be equal to 50 joule. So total heat rejected by the refrigerator will be how much? From conservation of energy, this heat is extracted by the refrigerator, and this is the work done on the refrigerator. So they will be added in total rejected heat from the energy conservation. So we can say that heat rejected will be equal to the work done plus heat extracted from the conservation of energy. So work done is 50 joule and heat extracted is 300. So you will get 350 joule. So my option number 4th will be the correct choice. Now let's move to the question number 36.